Hello. Yeah, I'm here to tell you a little bit about time travel and tracing. Hopefully it's going to be fun. But first I'm going to introduce myself briefly just to give you a bit of context on what I'm going to present and the motivation behind DejaView. So I am utterly uninterested in performance, which makes me a bit different from most of you, I suppose. But I work in security, actually. I work on kernel security for Google. I'm based in Zurich, Switzerland. And my area of focus is mostly hardening, which is about making kernel exploitation harder. And that tends to involve some low-level development, only boot bring up and stuff like that. And also fuzzing. And when it comes to fuzzing, we find a lot of bugs, and hopefully we try and fix them. But the kernel is a complicated beast. So this is a picture of me surrounded by various subsystems. And there's a lot. Bugs can be hidden in net, in memory management, performance, KVM, file systems, whatever, you name it. And yeah, it's complicated. And usually the bugs are at weird intersections of all these subsystems. So what I lack in depth of kernel knowledge, I try to compensate with good tooling. And I've invested a lot of my time in just generic kernel development tooling to help me do my job better. And so as part of that, I looked a lot into tracing, debugging. I obviously used a lot of ftrace, used a lot of GDB. And I was always wondering, is there some way to plug the two to sort of bridge the gap between these debuggers and my tracing experience? And let me start with a demo. So actually last week I presented a variant of this presentation to my team. And after the talk, they came to me and they said, hey, Florent, we didn't really get the point. So I figured I would start with the point while I have your attention, and then you can all fall asleep during the explanation of how this works. It's fine. So hopefully the demo is going to work, because there's obviously always the demo effect. So I'm going to demonstrate a little bit what is my development environment like. So I built this sort of a well-integrated kernel development experience that bundles a bunch of things together. And essentially what it comes down to is some IDE based on VS Code. And I can press a simple key. I just press F5. And what it does is it spawns a QEMU. And this is a run of my development kernel, essentially. Nothing crazy. I can kill the QEMU and that's it. Now, let me talk about DejaView. So as part of my development setup, I provide a bunch of tasks to build the kernel, to run it, to add debugger, whatever. And I implemented a new task called record and trace. And if you use it, you're going to see a similar experience as a normal run. You see QEMU starting up. You will notice it's a bit slower because it's actually recording everything that's being done and tracing it. So I'm gonna stop it here. And at this point, you see it reached the user space. That was the point where it was chaining into user space. So a bunch of things just happened now, and I'm going to walk you through them. So the first thing that happened is when I killed QEMU, it saved the trace of the run, and it immediately opened it within my IDE. So it's you may recognize some bits of the UI because it looks a lot like Perfetto. That's for a good reason. It started the trace processor to process the trace, and it opened the trace directly in my IDE. So if you're familiar with Perfetto, there's nothing new here. It's just split by threads. And if I open, for example, the swapper thread, I get a trace of the early boot stage of the kernel I just ran. So it helps me get an overview of what I just ran. So until now, looks a lot like a regular tracing environment. But there is some additional goodness. So let's have a look at a function like this PCI IOMMU alloc function. One of the things that DejaView adds to this UI is this debug button here. If you press it, there is an additional cursor that just appeared here, and it's actually a deterministic replay of the execution we just recorded that is actually executing the kernel once again. And when we reach the slice of interest, so the PCI IOMMU function that I just showed, it's stopping there, and it's attaching a debugger. And the debugger is being streamed to the trace visualization. So at this point, I have a bridge between the debugger. I get a live GDB experience with the view of my instructions and whatever, integrated in the trace visualization. So if I zoom into the trace up to the point that I attached, One thing you might notice is that the time axis on top doesn't look like milliseconds. It's actually instruction count. And so if I single step my kernel with, for example, step I, you will see the cursor move by one instruction. So you see overlay on the trace the current execution. And it gets even better than that because the execution is deterministic and replayed always exactly the same, you can use commands like reverse step I, which actually travels back in time. It will just execute the kernel once again, but stop one instruction back. And this is really powerful because it lets you reach a bug, travel back in time, see what caused the corruption, and inspect the state of your system. And so you sort of combine the benefits of the debugger UI, time travel, debugging, and a trace visualization across all threads in your system, across kernel space and user space, all of this integrated in your IDE. And because of the integration in the IDE, if you, for example, click on a function, like let's get back to PCIMMUalloc, you can look up the symbol in your development environment, for example, and it brings you to the code. So from the trace, you're also linked back to your development experience. So that's kind of the point. But I want to talk a little bit about how all of this works, and this is the part where you can fall asleep, if you like. So I'm going to talk a little bit about record and replay first, just to give you a sense of what this is about. Also known as time travel, debugging, and execution. So if you have a program and you execute it a few times, it will behave differently. The pointers will be different, the timing will be different. And when you debug some really nasty kernel bugs, it can be annoying that you're looking at a pointer value, and then on the next one it's going to be somewhere else, or the data corruption is going to happen somewhere else. All of this is quite annoying. But if you run in a runtime, where the runtime is able to record all the external input to the program, you can rerun the program and provide the same input that you recorded. And in this way, the execution will be deterministic. It will be always exactly the same. And by that I mean that the nth instruction, for example, the 1 millionth instruction of your run, is always going to be the same. The content of the register is always going to be the same. The memory is always going to be the same. And this is powerful because it gives you the impression to travel back in time. You can run it again and stop earlier in time to find what corrupted the buffer, for example. Yeah. So this is the concept of record and replay. It exists for user space, but QEMU implements support for record and replay in its TCG mode. So just a bit of background on QEMU. QEMU can work either as a virtual machine manager using KVM, which is hardware accelerated, super fast, or it can work as an emulator using something called TCG, Tiny Code Generator. And for example, if you run foreign architecture, if you run ARM64 guests on an x86 machine, you are using TCG to JIT the guest code into native code. And so in TCG single core mode, QEMU supports RR, so the ability to record external input and replay deterministically. And the replay can be controlled, for example, with GDB. I showed the reverse step I command, or with the QEMU monitor port, which is a TCP port that you can send commands to. So this is about QEMU record and replay. Now for something different. In TCG mode, when QEMU JITs basic blocks one by one, it's actually quite powerful because you can extend it with custom logic. You can write QEMU TCG plugins that can get called back every time QEMU translates a basic block from the guest architecture to the native code. Then from that callback, you can inspect all the instructions, and you can register callbacks for the execution of those instructions. And then from those callbacks, you can read the content of the memory, the content of the register at the time of the instruction. And this is really powerful because you can inline logic in between the instructions from outside the context of the guest. So you can freeze the execution of the guest, collect as much information as you need from your guest, and store it somewhere. So I use this logic to implement a QEMU TCG tracer. So it's a little plugin for QEMU that loads as a shared library, and it basically records every call and write instructions to generate a function call graph that works across the kernel space and user space. And it saves it to a format which is basically the Perfetto trace format. And instead of indexing the trace by time, which doesn't really make sense in an emulated environment anyway, it indexes the trace by instruction count. And so this closes the gap between record and replay and the trace. And one more thing I want to quickly talk about. As a virtual machine manager or an emulator, typically a guest is a black box. You don't really know what's going on in there. It might be Windows, might be Linux, might be anything. And so it's quite hard to figure out high-level states in the guest as a VMM. There's this thing called a semantic gap, which is as a hypervisor, you only have access to low-level states like registers and memory. But if you want to figure out what is the thread that is currently running in the guest, for example, then you need some a priori knowledge of what is the guest. And then you can walk through registers and memory and extract high-level states. So the Tracer plugin that I implemented has a Virtual Machine Introspection for Linux. So it's able to walk up registers and guest memory to figure out what are the threads that are running, when the context switch happens, and all of these things. So I talked a bit about QEMU, TCG, record and replay. I talked a bit about QEMU, TCG tracing. And now this is kind of the point I want to hammer, the reason why I'm here. It's just this concept of time travel tracing, which I think is quite cool. The way I think about it is that on one hand you have record and replay, so time travel debugging, which is super powerful because it gives you full introspection of the program state at any instruction. If you think about it, you have access to the whole memory, the whole content, register content, and it's really quite good when you can use it, obviously. Not all systems run in deterministic record, but for example, the bugs that I have that do reproduce in QEMU on single core TCG, which is most of them, then they get all of this value. So RR is really powerful, and on the other hand, you have tracing, which is immensely powerful at extracting a bird's eye view of your trace and extracting details out of a mine of information. And the way I see things, these two sort of complement each other really well. And if you close the loop between deterministic record and tracing, you can do some interesting things like iterative tracing. So the way I think about it, for example, is you record the first trace that is very high level. You only record, for example, context switches and the processes that are running across along the time axis. Then you can zoom into one process time slice you're interested in, and you can trace it again, but this time with a finer granularity. You could trace, for example, the function call graph, and then you can zoom in again and you can trace it again. And so you can sort of iteratively build a better and better trace as you explore the trace. So another thing that comes from the tracing ecosystem, and I'm very thankful to everyone here to contribute to the ecosystem, is the fairly mature ecosystem of toolings. And shout out to Perfetto, which is amazing. I benefited a lot from the architecture and the maturity of Perfetto, and it can do super smooth rendering of trace in a web UI. The architecture is really powerful because it's split in between the web UI rendering and the trace processor. And so, for example, it's possible to run the trace processor as a native process on one's machine, and the web UI will sort of connect to it through a TCP port, and all the processing, all the heavy lifting will be done in the trace processor. And so Perfetto is really powerful when it comes to performance analysis, but as I said, in my context, none of this matters, actually. I am not interested in Chrome, I'm not interested in Android, and I'm not interested in timing, scheduling time. All of these things is irrelevant to me. The only thing I'm interested in is insights into an execution to help me debug. So I made a little fork of Perfetto, and I want to explain part of the reasons why. One of the reasons why is that this is only a sort of 20% project that I'm doing on the side, so I don't really have the capacity to contribute much more than that. So that's part of the reason. And another reason is that the goals are somewhat different from Perfetto, the way I see things at least. Because my idea was to add to the Perfetto UI this ability to control a replay, see the cursor of where the execution is, and stream a debugging session, which maybe differs from the original intent of Perfetto. So yeah, DejaView is sort of this QEMU plugin that traces things, and this glue that brings together the record and replay ability with the web UI visualization. So hopefully now you get a little sense of how this works and what it looks like. So I wanted to tell you a little bit about some of the use cases that we found so far. So the main use case that I have, the reason why I brought this up, is for my own development needs. So as part of my development environment for kernel development, I have a very well integrated way to just record a trace and visualize it immediately. It's just one key press away, which is really nice because that means I don't have to think twice and set up a whole complicated system. I just press the key, get the trace, and it doesn't break my thinking flow. And yeah, this ability to close the loop between the trace and my development environment, this has proven quite useful. So to implement this, I had to write a VS Code plugin, which basically opens the trace files. So if you open one of those trace files in VS Code, it will spawn a trace processor and takes advantage of the fact that VS Code is a web UI. And because Perfetto is a web UI visualization, it can immediately open the trace within the IDE. So that's sort of the first use case. One of the reasons why I built this is because I work a lot on sysbot bugs. So sysbot is a continuous fuzzer that continuously finds C programs that crash the kernel. And this is where I spend a lot of my time trying to look into those bugs. So there's also a little bit of automation there that I wrote a little script that if you give it the URL of a sysbot bug, it's able to fetch the kernel that was used to cause the bug. It's able to fetch the reproducer, the C user space stimulus that causes the bug, and it's able to record the deterministic record and trace of the execution, and then you can open a trace, time travel, and immediately get insights into the bug. And one thing that's kind of fun to think about is because sysbot has a web site in which you can see all the crash reports, they could actually also visualize the traces directly there in the web UI with Perfetto, in addition to the backtrace at the time of the bug. So not only kernel developers could get the backtrace at the time of the crash, but also a visualization of whatever happened before, which I think will be quite cool, but we'll see if the sysbot team is interested in this. And one more use case, which is again kind of adjacent to everything I do. Some of my colleagues in Zurich work on a program called kernel CTF, and what they do is they run a vulnerability reward program where they pay external researchers for exploiting kernel vulnerabilities. So my colleagues receive various exploits, and they have to assess them, figure out how they work, to give some rewards to the external researchers. And they have also found that the DejaView plumbing helps them a lot to just put the exploit and the kernel that was exploited in the box, and then they immediately get pretty deep insights in what is going on in there. So yeah, that's basically it. The code is open source, it's available on my GitHub. If you want to have a look, you are free to run it. And hopefully it sort of inspires you to not only look at kernel development or QEMU, sort of full system RR, but also I think it might be interesting to think about user space, RR, and tracing. I think there are opportunities for variants of this project that would maybe fit your need better, or fit most needs better even. Yeah, that's it.
That's really cool. I love the workflow. When you compile your kernel, how big is that file? Like when you're running that, how big is that file if you have all the registers and the trace?
So there are two files, right? There is the record, which is the QEMU.
The QEMU record. How
QEMU record is basically nothing because
Wow.
replay.bin. So in this case, it's 13 megabytes, which is actually huge. Usually, it's maybe I forgot to flag to QEMU or something, but it only records the external input to the system. So it can be, for example, time register reads or disk I/O, but it's actually fairly small. Yeah, so you only save the external input, which is quite small.
Then you replay.
And then you replay, yeah.
Beautiful.
Yeah.
How do you get the instruction count? Is it in the callback from QEMU TCG?
Right, so as part of my QEMU TCG plugin, I count instructions. and it's actually quite cheap because they have this concept of scoreboard in QEMU TCG plugins, where you can think of it as an additional microarchitectural state. You can sort of extend the CPU, the virtual CPU architecture, to have counters, for example. And all of this logic gets inlined in the JITted code. So when QEMU JITs a basic block, it will basically JITs the native instruction for the emulated instruction and an increment of a counter. So as part of the running the basic block, the counters will be incremented.
And in the command you get back that counter and so
Exactly. So when I reach a call instruction, then it calls into my code, and from that code I can read the scoreboard, the thing that was incremented, and I can record what is the address that is being called, what is the current instruction count, and later on format it into the Perfetto trace.
My question about the rate for replay. So, for example, if you want to go back to a certain instruction, so does it like rerun the entire program from the beginning, or just?
Yeah, so that's a good question. I'm not sure if I'm supposed to repeat the questions for the microphone. I'm going to repeat it.
Yes.
Ideally, yes. So I should have done it before. Sorry. The question is whether deterministic replay has to always start from the beginning. It doesn't have to, because you can take snapshots at different instruction count, and then it only has to replay from the last closest snapshot in the past. So it's a bit of logic that I haven't had time to implement, because obviously, like all demos, I finished them yesterday. But it's actually somewhat trivial at this point to extend this setup such that from the UI you could click on the slice and say, add a snapshot here, and then all the further replays will start from that snapshot, so you don't always have to go back from the beginning. And the reason why in my demo I took a fairly early boot function is because I didn't want to wait for the full thing to replay, just for the sake of your time. But you could add snapshots wherever you want. For example, at the end of the boot, when you change into user space, or I have the plumbing to reproduce only Sysbot crash reproducers. So for example, taking a snapshot at the beginning of the user space stimulus, and then only replaying those syscalls that matter. Stuff like that. Everything is possible now.
Thank you.
Yeah.
Yeah, I know the spam mails of the Sysbot when it detects some crash, and sometimes they said the Sysbot have not found reproducer yet. So you telling me soon, or it's already happening, that Sysbot is telling me some commands I can run and go back in time to reproduce these issues that didn't have a reproducer yet.
So just to be clear, the Sysbot team hasn't committed to using any of that. This is my sort of side pet project that helps me debug things. But I work with them regularly and they are interested. So I don't know, maybe someday it will end up, if you tell them, maybe it will end up on their roadmap. So you're asking whether Sysbot will fuzz in a deterministic environment, and it doesn't, because the deterministic environment is a bit slower. Maybe you notice that the boot with KVM acceleration took, I don't know, like 5 seconds. The boot with the record and the tracing. So the difference between KVM, virtual machines and TCG emulated machines is maybe slowed down by 4 or 5. And so for Sysbot, it makes sense to fuzz on either native machines or in KVM. It doesn't really make sense to fuzz in TCG. But what they can do is they can fuzz on KVM, so non-deterministic environment, and then try to call the reproducer in a deterministic emulated system. And if it does reproduce there, then they can provide you with a deterministic record of that bug. But there will always be bugs that, for example, need more than one CPU, in which case they wouldn't reproduce in this environment, or for some reason they rely on some behavior of KVM emulate, like virtual machines or something like that, and then they won't be able to use a deterministic system all the time. Any more questions? Yeah.
Maybe it's a general question is, I don't understand how it's possible to be so small, because I was thinking naively you need to dump all the memory of user space, because you don't know which memory user space will use, so you have a way of knowing which user space memory you will be required to replace the trace. This is why you don't need to dump everything.
So if you think of the question is, how can the deterministic record be so small?
Yeah,
that's the question. And why don't we have to save all the memory? If you think of your emulated system as a black box, you can limit all the external input to the black box, right? So you can enumerate all the external inputs that change the state of your machine. So, for example, the time register read. When you do a record, QEMU will trap every time the guest tries to read the current time, and it will save at this instruction count the guest tried to read the time, and the reply was this. Or, for example, if you have a hardware random number generator, you can remember the output all of those external inputs. And then if you play it again and you provide the same random number generator seed for the same time, everything will behave exactly the same. So you don't have to save anything from user space. You will just run the user space again with the same random seed, the same timing counts, and everything will behave the same. The scheduler behavior will be the same. So yeah, everything is stable. And then to get access to the user space memory, you just have to run it again.
Yeah. Thank you.
Anything else? All right, time for lunch.
Focus.